Okay, so let E be an elliptic curve over Q which does not have complex multiplication, and let n bigger than or equal to 1 be an integer. Now, since E is defined over Q, we have a natural action of the absolute Galois group of Q on the set of n torsion points that gives us a representation rho sub comma n. And if we choose a basis for the n torsion points, we can identify automorphism of En with Z to Z mod nz. And okay, so that's at level n. And if we choose a system of compatible bases for all the ENs, we can combine these representations to get a full Eilich representation. It's a very famous theorem of Serre that the image of rho sub E is an open subgroup of GL to Z hat with full determinant. I'm sure most of you are familiar with Mazur's program B, and that it's a very hard problem to give a description of images of rho sub E. So the reason why modular curves are interesting objects to study is because the points of these curves are elliptic curves, and they contain additional information about their associated Galois representation. So I'm going to give a brief introduction to modular curves in this slide, and I'm going to talk about them in detail in coming slides. So let me fix an open sub of GL to Z hat with two conditions: that it has full determinant and it contains negative identity. And the level of G is the smallest positive integer n, such that when you project GL to Z hat to GL to Z mod nz and you take the inverse image, you recover the full group G again. So associated to this group, we have a modular curve xg, which is a nice curve over Q. And by nice, I mean it is smooth, projective, and geometrically irreducible. And it has a morphism pi g from xg to p1q, which is also defined over Q. And as I said, those parameterized curve is that the image of rho sub E is contained in G transpose. And to quantify what loosely means, I mean that if you have an elliptic curve over Q such that its J invariant is not 0 and 1728, then the image of rho sub E is conjugate to a subgroup of G transpose if and only if its J invariant lies in image of this map pi G. So in the previous slide, we associated a pair xg pi g to G. And the problem I want to talk about in this talk is, can we have a classification of all genus 0 modular curves with a rational point? The answer is yes. And I must mention here that there is a classification of genus 0 and genus 1 modular curves of prime power levels, which have infinitely many points due to Professor Sutherland and Professor Zivina. And why genus 0 and genus 1 curves are interesting is because these are the only two curves that can have infinitely many points. And to have information about them, like saying that a curve has infinitely many points, means that you have infinitely many curves that have their image of associated Galois representation inside your fixed group. And these kind of data can be interesting in studying various problems. So I'm looking at genus 0 curves in this talk. So if I want to classify them across all the levels, I'm not restricting the level. There are definitely many of them. So let us see a family of examples, and it will be clear why it is a quadratic family. Okay. So family is going to be parameterized by a square-free integer d. For each d, I have an associated open index 2 subgroup G sub d, and the associated modular curve is P1 of Q. And the morphism pi GD is described by this rational function. T goes to dt square plus 1728. Now, a cute observation here is that if you take that any rational number can be expressed as dt square plus 1728 for some t, for some rational t and some square free integer d. Okay, so that's the reason why the representation rho e is never surjective. So for every elliptic curve, you have this constraint given by this degree 2 map. So these groups GD are non-conjugate. These curves are really different over Q. Their images are different, but there is something nice that happens. If you take the quadratic field Q at joint square root of D, these curves are twists of each other over this field. And what I mean by a twist is that there is a morphism, there is an isomorphism xt to xt1 such that this diagram is commutative. Okay. And for each d, if I look at the congruent subgroup GD intersected with SL2Z, I get a unique index to congruent subgroup every time. So all these GDs are coming from the same congruent subgroup. And this is the idea which I will exploit in like giving my classification. Okay. So the theorem is that we can classify all the genus zero modular curves with a rational point, finitely many explicit families. And let me also give a cubic family of modular curves here. So again, this is parameterized by rational numbers. So xv is p1 of q with the morphism sub v described by this not very nice looking rational function, but this is as simple as I can make it. So this describes a modular curve, and moreover, given a v, if I fix a v, I can explicitly compute the generator for the group G sub v corresponding to this pair xv pi v. And similar to what we saw in quadratic case, this xv pi v is a twist of this fixed curve x3 comma 2, x3 by 2 comma pi 3 over 2 over a cubic field now. Earlier we had quadratic field. This is a cubic field, q adjoint alpha, where alpha is a solution of this explicit cubic equation. Any questions so far? Am I okay so far?
There are no questions so far. You're good.
Okay. So let me give a more concrete definition of modular curves. So I use, like, for computing modular curves, I use description of their function field. So my definition is also in terms of function fields. I'm not using Deligne-Rapoport definition. I'm not describing them in terms of stacks or anything. One be an integer, and let gamma be a congruent subgroup. And h upper star is the extended upper half plane, and x sub gamma is the complex curve, gamma acting on upper half plane. And when gamma is the principal congruent subgroup, we use the notation xn for this complex curve. Okay. So if I take the set of all meromorphic functions defined on this surface xn, such that all the coefficients of its Q expansions lie in this nth cyclotomic field, then that is a field. I have a field of meromorphic functions, and I call that with f sub n. Okay. If I take n equal to 1, then that is generated over Q by modular J invariant, where the Q expansion of the first few terms of its Q expansions are this. Okay. And if n prime divides n, then we have an inclusion of fields. F sub n prime is contained in f sub n, and we have that every f of n contains f of 1. So for groups, I suddenly move to this very odd looking field. There is a connection between them. The connection is
Rakvi?
yeah.
Okay, I couldn't hear you.
Is it okay now?
Yes, it's okay. I'm not sure if I lost you a little bit at the end of the last slide.
Oh, should I say something again?
You said something about some strange looking field, and then it stopped for a little bit.
Oh, okay. Oh, so nothing was lost mathematically. I just said that suddenly from matrix groups, I described this field. What's the connection between them? The connection is in the next slide. So I have this inclusion of fields. F1 is contained in F sub n. This field extension is Galois, and this the Galois group is isomorphic to GL2 Z mod NZ, modulo plus or minus 1, because they act trivially. I have not described the action here due to lack of time, but we have this isomorphism. And the cyclotomic field is algebraically closed inside this function field. Okay, so what is my curve then? So again, G be an open subgroup with satisfying those two conditions, and n is the level of G. The modular curve xg is that curve over whose function field is the subfield of Fn fixed under G. Okay. And I have inclusion of fields. F1 is contained in this function field Fng. And this inclusion gives me the morphism between curves xt to P1 of Q. Okay. Now, just to recall, what are the points of this curve? The points are those elliptic curves whose associated Galois representation is contained inside Z transpose. Okay. So let me discuss how these modular curves are connected to congruence subgroups. So if G is an open subgroup of ZL to Z hat, then if I intersect that with SL to Z, that's a congruent subgroup. But the catch is that their levels are not same. Level of gamma divides level of G. Okay. But they are naturally isomorphic over G, so their genus are same. And there is a nice thing about congruent subgroups is that if we fix G, then there are only finitely many congruent subgroups such that X sub gamma has genus G. And for genus between 0 and 24, there is a complete classification available in Cummins Poly database. This is the link. But as we saw in a couple of examples before, that we can have infinitely many modular curves xt of a given genus. So in general, what happens is given a congruent subgroup of level m, there may exist infinitely many G, again satisfying those two conditions, whose level is a multiple of m, but they are all coming from gamma. Their intersection is with SL to Z is gamma. And these curves are not all the same. That means that they are not isomorphic over Q. The sets may differ, but they all become twists of each other over cyclotomic extensions. Okay. Any questions so far?
Nope, looks good.
Okay. So let me describe how do we actually classify these things. So I fix a genus 0 congruent subgroup containing negative identity. Let's say it has level m. And a goal is to compute all the pairs xt pi g such that xt has a rational point, which means it's P1 of Q. And G comes from gamma. That is G intersection SL to Z is gamma. Okay. So now for this fixed congruent subgroup, and there are, you can look at Cummins Poly database. I think there are 120 or 121 genus 0 congruent subgroups. So for each one of them, what I do is compute an explicit modular function H that lies in F sub M. I would like to recall F sub M was the field of meromorphic functions defined on X sub gamma, whose Q expansions had coefficients in case. Okay. So I compute an explicit modular function that is a generator for function field that generates the function field of X sub gamma. Okay. Our H is a Hopf module of gamma, which is given explicitly in terms of Siegel functions. Compute such an Hopf module, I compute a rational function with coefficients in K sub M that sends H to the J invariant J. Okay, it's a function defined on generator. So this function describes the morphism between curves X sub gamma to P1. Okay, but this has coefficients in K sub M. We are done. Once we have a map pi sub gamma, what I do then is search for a modular curve xt0 pi g0 over Kn, where n is a multiple of m. And I want xt0 to be isomorphic to P1 of Kn, where P1 of Kn is the curve function field Kn adjoint H, where H was the Hopf module. Okay. And I want these curves to be isomorphic in such a way that F should make this diagram commutative. Okay. Pi g0 is defined over Q, but pi sub gamma has coefficients in the cyclotomic field. So this commutative diagram gives us a condition on F inverse of sigma F that it must satisfy. Okay. So it is a twist, and they have a condition on co-cycles. Okay. So the map described previously that sends sigma to F inverse of sigma F is a one co-cycle. And once I fix some n, there are finitely many of them. with this cocycle is that this cocycle gives me a twist of P1 of Q, okay? That can be explicitly computed as a conic, and then we can check if it has a rational point. If it is a rational point, then I know my curve xt0 pi g0 is P1 of Q, okay? Great. And then once I check that my conic has a rational point, then I compute a matrix that realizes this cocycle as a co-boundary. Okay, and composing that with pi sub gamma gives me the map pi sub g0 corresponding to that. Okay, and from this information about the cocycles and using the hop module, I can also compute a set of generators for g0. And I do this for every convex group, and this process terminates like either I have that there are no g0s that exist, or if they exist, I can find them at base level itself. So this step terminates. So once I have something to start with, once I have a curve xt0 pi g0, then I search for modular curves such that xt and xt0 are twists of each other over the maximal abelian extension of Q. Okay, and again, I want the isomorphism such that this diagram is commutative. So this gives me a condition on the cocycles. So given a cocycle, again, what I described before, I check if the corresponding curve xt is P1 of Q. And if yes, then I compute the map down to, and I compute the map pi g. And so let me define set. Let me give a name to this condition here that I have in the bottom of the slide. So automorphism of xt pi g is the group of all automorphism of xg which preserve the map pi g. Okay. So basically, the last slide said that the cocycle should be, the image of the cocycle should be inside automorphism xt pi g. Okay. And the set odds q xt pi g are all those automorphisms inside odd xt pi g which are defined over q. They are not defined over higher fields. Okay. Now what happens is that after computing the finite number of twists xt pi g isomorphic to xt0 pi g0, all the other modular curves that can come from this gamma and are isomorphic to P1Q, they come from the cocycles that land inside this group defined over Q. Okay. So now the action is trivial on this. So the cocycles become homomorphisms. Okay. And that's where the description of family comes from. The cubic family, which I described before, it arises when odd sub q xt pi g is defined by cyclic of order 3, explicitly given as this. It's unique up to conjugation. Now for the last slide, I'm going to use the notation fancy A for this odd sub q xt pi g. So the classification breaks down depending on what fancy A is. So fancy A can be of order 1, it can be of order 2, and these two things are non-conjugate because if alpha is not a square, then it's not conjugate to t minus t. So they are two different things. And fancy A can be cyclic of order 3 given as this. This is unique up to conjugation. So everything can be put in this form. Fancy A can be cyclic of order 4 and up to conjugation it looks like this. And fancy A can be clan 4 group. But clan 4 group can have different, like up to conjugation in PGL2Q, there can be different kinds, and I have given some examples. Okay, so the classification breaks down. Thank you.
Okay, thank you.